Hello everyone, I'm your TA Jiawei Wang. This is a special discussion section. I made this video clip to explain some problems in trig substitution and partial fractions. Okay, let's get started. So for trig substitution, the most two important identities we're going to use are sine theta square plus sine theta square equals 1, and the other one is tangent theta square plus 1 equals secant theta square. Right, so these are very important identities for trig functions. So how do we use these two identities for trig substitution? Okay, so let's jump to conclusion first. So basically there are three kind of trig substitutions. For a minus bx square, so suppose there is part of the formula which is in this form, like under the square root, the formula is a minus b times x squared. So here a and b, there are two positive constants, and x is a variable. The idea of trig substitution is we want to get rid of the square root by using some trig functions. So how to get rid of this square root? So basically we are going to use the substitution x equals square root of a over b sine theta. Okay, so why do we use that? Because if we use this formula becomes, maybe plugging x equals this into x, right? This one equals a minus b times this one squared. So this one is square root of a over b sine theta square. Right, I just plug in this one into x. Okay, this one equals a minus b times, okay, this one is a over b sine theta square. Right, this one is basically a, you can take out a, and this is 1 minus sine theta square. Right, this one basically is a times sine theta square. Right, this one basically is square root of a times sine theta. And it is best to keep the absolute value for now, because we don't know like the range of x, and based on the range of x we can figure out what is the range of theta. So yeah, just for now let's keep the absolute value. Okay, so basically if you have a form like square root of a minus bx squared, for a and b are both positive, so use this trig substitution. Okay, so how to come up with this substitution? I think the idea is you can first make this constant a to be 1, not for free, but try to make this constant 1, so you know like which one of these you want to apply for the trig substitution. Because here, right, you can see like something square plus something square equals 1, or something square plus 1 equals, right, something square, right? So in these two identities, the constants are 1. So here a is a constant, right? So we make this constant 1, so we can figure out what should be used in the trig substitution. Okay. Okay, so basically here is the formula, right? Square root of a minus bx squared. Okay, so our idea is to make this a equals 1, but not for free. Okay, so how to make that 1? So basically you take out a, and the rest of it is 1 minus b over ax squared. Right, I didn't change the value, I just take this a out. Like a is a common factor in this formula, and the second term becomes like b over ax squared, right? The first term becomes 1 because a is a constant, so we can take the constant outside of the square root, right? A is a positive constant, and this one is square root of a, right, times square root of 1 minus b over ax squared. Okay, so now here is our constant 1, and basically I want to use the identity, right? Sine square plus cosine square equals 1. So basically I want to use 1 minus sine theta square equals cosine theta square. I want to use this identity. Right, why do we use this identity? Right, this is 1 minus, right, something equals some square, right? We want to make the whole thing in the square root equal something squared, right? So basically this 1 minus this whole thing, right, b over a times x squared is sine theta squared, right? So basically we let b over a x squared equals sine theta squared, right? Because if we let this one equals sine theta squared, then right, this thing 1 minus b over ax squared equals cosine theta squared, right? So we can take out this, remove the square root. Right, keep the absolute value for now. Right, we use this identity, so we know like 1 minus the thing, right? 1 subtract this thing equals sine theta squared. Or you can use cosine theta squared, it doesn't matter. So I just use sine theta squared for now. So this is the trig substitution. So basically you can solve for x, so you know the actual trig substitution. Right, this is the trig substitution. We need to solve for x. And so we move this b over a to the right hand side. So x squared equals a over b sine theta squared. Then we take the square root. X equals square root of a over b sine theta, right, by taking the square root. Right, this is the same, right, same formula in here. Okay, so this is basically the first type of trig substitution. If you have a form of square root of a minus bx squared, then the trig substitution is x equals square root of a over b sine theta. Yeah, actually you don't have to remember this because you know it's easy to like derive this trig substitution by using such trick, right? By making the constant term equals 1, so you know like which identity you are going to use. Yeah, but okay, so I'll write the conclusion for now. Okay, for this form, 1 square root of a minus bx squared, we use x equals square root of a over b sine theta, or x equals square root of a over b cosine theta. They both works. Or in this form, ax squared minus b, the trig substitution is x equals square root of b over a secant theta. Or the last one is for a plus bx squared, then the trig substitution is x equals square root of a over b tangent theta. Yeah, these are conclusions. Basically, it means if you see, right, if you see some such type of formulas in the integral, so one possible way to solve it is using trig substitution, because by using trig substitution we can get rid of the square root. Yeah, of course you may get some square root of this, but this is only a constant, so we get rid of the square root in terms of the variable. Basically, there is no variable under the square root. Yeah, actually you don't have to remember these three, because I don't remember these three. Right, you can easily derive these three by using, like, you can make the constant equals 1, right? For example, here you can make a equals 1 by taking a outside of the square root. Similarly, here b is a constant, so you can take out a square root of b outside of the square root. Here, similarly, a is a constant, so you can take out an a outside of the square root. Okay, let's move on. Let's look at some problems. Okay. Example, integral of 1 over square root of 4x squared plus 1 dx. Okay, so this is a formula. So we observe there's a square root, right? Under the square root you have 4x squared plus 1. Right, since this 1, right, it is already 1, right? So we can apply the one identity, right? Basically we want, right, the idea is to write 4x squared plus 1 into, right, something squared, right? And there is one identity, right? So you have tangent x square tangent theta square plus 1 equals secant theta square. And this is one identity. And basically 4x squared is the tangent theta square, and this one, the right hand side, is secant theta square. So basically we 4x squared equals tangent theta square. This is a trig substitution we are going to use. Right, so we can solve for x. So x equals x squared equals tangent theta square over 4. So x equals 1/2 tangent theta. Right, basically this is the trig substitution we're going to use. So if x is this, then the derivative, we need to rewrite everything, right? Rewrite everything in terms of the new variable theta. And here x is the original variable and theta is the new variable, right? So we need to rewrite dx in terms of theta. Right? X is 1/2 tangent theta, so dx is a derivative of this, right? It is 1/2 secant theta square d theta. Okay, so we plug this one back here. Okay, we plug in this here, so we get just copy it here. Okay, we plug in. So it's integral of 1 over this thing. Okay, this one is okay. So this is our trig substitution, right? So if we use this trig substitution, then 4x squared plus 1 equals, right, secant theta squared. Right, so here we have secant theta square times dx, right? dx is this, right? Times 1/2 secant theta square d theta. Okay. Okay. By taking this, we can move constant here, and the numerator is secant theta square, and denominator is, right, is not only secant theta. It is best to write absolute value here. And because when taking out the square, we have to make sure, right, this one is positive d theta. Okay. And this one, right, you can write in this way. Right, depends on the sign of the secant theta. Right, it's either positive or negative, right? Then, right, after simplifying, you get secant theta with absolute value. Okay, and after this, right, if you know, right, if you know, like secant theta is positive, then this one equals like 1/2 secant theta d theta, and the antiderivative of secant theta is ln, right? It's ln secant theta plus tangent theta right, plus c. Right, if this one is negative, you need a negative sign. Okay. Okay, so because this is plus 1, right, so something plus 1 is something squared, so we should use tangent theta squared plus 1 equals secant theta squared. Okay, let's move on to the next problem. Okay, this one. So the integral 1 over square root of 25x squared minus 1 dx. Right, this is something square minus 1. Right, so right, the idea is 25. Right, we want to write this thing equals something squared. Right, so what identity should we use? Right, so if we use, basically it's the same identity, right? Tangent theta squared plus 1 equals secant theta squared, right? Yeah, we just move this 1 to the right hand side. So basically we're going to use secant theta square minus 1 equals tangent theta square. And we use this identity, right, because this constant is already 1, right? Okay, so basically this one, 25x squared, is our secant theta square, right? The right hand side is tangent theta square, right? So we are going to use 25 x squared minus 1. Okay, 25x squared equals secant theta square. So we have x, you can solve for x, right? X is 1 over 5 secant theta. Right, move this 25 to the right hand side, and then you take the square root. Right, x is 1 over 5 secant theta. Oh, actually, there is one thing I forgot to mention for the previous problem. Right, this one, right, this is the antiderivative, but it's not the final solution, right? Because the original variable is x. Right, the original variable is x, but here we use theta, right? So we need to rewrite, right? We need to rewrite this thing in terms of x, right? Because we use the trig substitution, x equals 1/2 tangent theta, right? So this one tangent theta is 2x, right? So here is 2x, but what about secant theta? And basically we can use the trig identity, right? Secant theta square is 1 plus tangent theta square. Right, so tangent theta is 2x, so it is 1 plus, right, 4x squared. Right, so secant theta is, right, square root of 1 plus 4x squared. Right, so tangent theta is 2x, secant theta is, right, square root of 1 plus 4x squared. Right, we plug these two back here, right? So final solution should be 1/2 ln plus 4x squared plus 2x plus c. Right, this one should be the solution, right? We need the original variable. Okay, let's get back to this problem. Okay, so this is a trig substitution. And what about dx? Right, dx is 1/5, right? The derivative of secant. Derivative of secant is secant times tangent. Is secant theta tangent theta. Right, this is our trig substitution. And we plug this one right back in here. Let's start a new page. Okay. 5x squared minus 1 dx. Right, don't forget dx because we need also to rewrite dx in terms of theta. Right, so we use x equals 1/5 secant theta, and dx is 1/5 secant times tangent. Okay. This one is write everything in terms of the new variable theta. This is 25 times x squared. X squared is 1/25 times secant theta squared, minus 1. Minus 1 times dx. Dx is this, right? Dx is 1/5 secant tangent, right, d theta. And this one is square root of 1 over secant theta squared minus 1 is tangent theta squared. Okay. And we can move this 1/5 in front. It's secant theta tangent theta d theta. Okay. What's next? So let's just assume, right? Assume tangent theta is positive. Okay, so make things easier. Okay, let's assume tangent theta is positive. So this is 1/5, 1 over tangent theta. Yeah, I mean this is indefinite integral, right? So we don't know the bounds on x and we don't know the bound on theta. But when you compute the definite integral, right, you know the bound on x, so you know the bound on theta, so you know whether the tangent theta is positive or negative. Right, so but yeah, for now, for simplicity, just use tangent theta is positive. Okay, secant theta, tangent theta, d theta, right? Okay, so this tangent theta cancelled. So this is 1/5 secant theta d theta. Right, the antiderivative of secant is right ln secant plus tangent plus c, and we need x back, right? You can use identity like tangent square plus 1 equals secant, or you can draw a rectangle, right? You can draw a right triangle, right? This is a right angle, and this is theta. Yeah, because we can draw this right triangle. Basically, it means we assume tangent theta is positive, right? Everything is positive, x is positive. So this one is theta, and we know secant theta is 5x. Right, secant theta is 5x. So what is secant? Right, secant is 1 over cosine. Basically, secant is this one over this one. Right, so basically, this is 5x. Right, this is 1. Right, so we have secant theta is this one over this one, so it's 5x over 1. Right, this is 5x over 1. So this one, so secant is hypo over adjacent. Right, so this one is 5x, this one is 1. Right, so secant theta is 5x over 1. So what about tangent theta? Tangent theta is this one over this one. Right, tangent is opposite over adjacent. Right, so what is this one? This one is square root of 25x squared minus 1. Right, this is a right triangle, so you know these two sides and you can compute these sides. So tangent theta is this one over 1. So basically it is 25x squared minus 1, right, over 1. Right, we write everything using x. It is 1 over 5 ln. So secant is 5x, right? Tangent is this plus c. Okay. So just summarize. Right, this is the trig substitution we're going to use, and it depends on the constant terms. Right? If you make the constant terms equals 1, right, by taking out some constant outside of the square root, right, you can make the constant term equals 1. But you don't have to remember this. After you make the constant term equals 1, right, basically choosing one of these, right? Right, these are two most important identities we're going to use. Right, use one of these to get rid of the square root. Okay, let's move on. Let's move on to partial fractions. Actually, partial fractions is not just for integral. Right? Basically, partial fractions is like a general trick for solving like a formula in a fractional form, and both numerator and denominator are polynomials. Okay, let's look at some example. Okay, 5x plus 1 over x squared minus 5x minus 14 dx. Okay. And this is a fractional function, and both numerator and denominator are polynomials. And partial fractions is we want to rewrite this function into like the sum of some simpler fractional functions. Right. The first thing we need to do is to factor the denominator. Right. The denominator is x squared minus 5x minus 14. Right. This is the denominator. Right. This is a quadratic function, and this is x. And this is 14. Right, so you have a 7 and 2 as factors, and 7 minus 2 is 5. So basically you have a negative 7 and a positive 2. Right, that's the first thing, to factor the denominator. Right, the second thing is, right, our goal is to rewrite this function into like the sum of some simpler functions. Right, what are these simpler functions? We are going to use this factorization. The denominator are these factors. Right, something over x minus 7 plus something over x plus 2. Right, so here we use a and a b here. And here a and b are two constants but unknown. So a and b are two unknown constants. We're going to find out what is a and what is b. Right, because the denominator is linear. Linear means having degree 1. Right, x minus 7. So here the denominator is quadratic, so has degree 2. But here the degree is 1, so the numerator always has one less degree than the denominator. So the numerator should have degree 0, so which is a constant. Right, constant has degree 0. Okay, we're going to find out what are a and b. So how to find out this? Because this is an identity. So basically a and b are constant, which makes this one an actual identity, an actual equation. Right? A and b will make left hand side equals right hand side. So we find a common denominator. Basically, we combine these two terms. Right. So it's x minus 7, x plus 2. Right. The first term is a times x plus 2. The second term is b times x minus 7. And just simplify this by finding the common denominator. Okay, we keep simplifying this, and the denominator is this, and the numerator is like ax plus 2a plus bx minus 7b. just keep in mind a and b are constants, so only x is a variable. So we just combine the terms with x and the terms without x. Ax and bx are linear terms. 2a minus 7b are constant terms because a and b are both constants. Right, so it's a plus b times x, right, plus 2a minus 7b, constant term. Okay, the left hand side is, I just copy it. Right, left hand side, just copy it down here. Okay, a and b will make this an actual equation, right? Denominator are the same, so the numerator should be the same. Right, so 5x plus 1 should equal to, right, a plus b x plus 2a minus 7b. Right, we compare the coefficients, right? The coefficients of the linear term and constant term, right? 5x is a linear term on the left hand side, right? The term with x, right? This one is a linear term of the right hand side, right? Linear term. So 5x should equal to a plus b times x, right? So 5 should equal to a plus b, and 1 should equal to, right, this one, 2a minus 7b. Right, you compare the coefficient on both sides, right? They should match. Right, the constant term equals constant term, linear term equals linear term. Right, so this is a linear equation, and we want to solve for a and b. For example, we can multiply, right? We can multiply the first equation by 2, and we subtract basically this one minus this one, so we can cancel out a, so it's 9 equals 9b, right? This equation minus this equation, so you get 9 equals 9b, so you get b equals 1, and you can plug in b equals 1 to here, so a is 4. Okay, so after solving a and b, so basically we rewrite this function, this fractional function, into two simpler fractional functions. Right, because these two are easier, so it's easy to integrate. Right, because, right, the degree is lower, right? The degree of the denominator is lower. Right, so the integral of this function equals, right, the integral of this plus the integral of this. Right, we love summation in integral, right, because we can separate them. Right, so this one, right, this one is ln, right, 4 times ln x minus 7, right, plus ln of x plus 2 plus c. Right, don't forget the constant c. Okay, for partial fractions, right, the most important thing is to factor the denominator and then write such equation with unknown variables, and then after that you simplify the, right, basically cross multiplication, and then compare the coefficient of the numerator. Compare the coefficient of the constant term and the linear term, and then solving a linear equation. Then you can write the original function into simpler functions. Then it's easier to do the integral. Okay, I think that's all for today, and I hope you will stay safe, and good luck to the final, and hope you have learned a lot of the integrals. Okay, thank you for listening. Bye.